So the original intent was to kind of give a demo how to use machine learning, go into some neural networks, deep learning. And last night I was like, you know what? Screw it. We're going to build Skynet. So this is going to be, I know everybody has laptops, so I want full engagement. Pull your laptops out. Even if you aren't going to follow along with the code, at least clone the repo so you have something later and you can walk through the code with me. So by the end of the night, I have 7 steps to build Skynet with pictures, and by the end of the night, we should end up with something like this. This is the goal, and if we don't, I'm disappointed. But not for real. We're actually going to do the boring thing, where we're going to predict diagnoses for breast cancer using deep neural networks. So still pretty cool. It's not Skynet cool, but it's neat. And down on the bottom left, there's a short link right there. That's the repo for the code that I'm going to go over. So if you want to be able to clone it, or you want to be able to play along. If you want to be able to play along, then that's where you're going to go. So one of the biggest issues preventing people from getting into machine learning is kind of this mental block. People think, okay, I've had some experience with Python. Maybe I've done a little bit on the computer science side, but machine learning, that's so far out there. That's so far beyond me. And that's really one of the things that I want to dispel today. Is it's really not, especially with the modern libraries and frameworks that we have, machine learning has become more and more democratized and much easier to implement than it has been historically. So to really get an idea of what machine learning is, what we're going to do today, I wanted to drive a little bit more into the history and the theory. So initially, the original intent of machine learning was to mirror the biological brain. So we thought, hey, here's what a neuron looks like. We have dendrites that connect to other neurons. We have the axon that connects to axon terminals that connect to other neurons. And the idea is, and we knew this long, long ago, that we learn through reinforcement learning. So when we're born, we see our parents' faces. Our brain processes that. We don't know what that means. But we get fed, we're held, we're nurtured, and we know that that's good. So we learn people, our parents, are good. But then as you grow older, you might see fire. And you see a fire, you feel the heat on your skin, your brain processes that, and maybe you're still super young, you don't understand until you get burned, you get a little too close, and that's still reinforcement learning. You have that negative consequence that your brain identifies, hey, that's bad. You don't know what that means, but that's the general idea. So the original pioneers of machine learning wanted to mirror that. They wanted to see if they could do something similar using analog technology. And that came about, that's how the Perceptron came about. So this is a Perceptron right here. You'll see that it matches the neuron pretty closely. So we have our inputs on the left. We have some type of function in the middle that goes into an activation function that gives us an output. This is super simple theory. We had this way before we could ever do it or process it through computers. And this is what a lot of people thought was going to be the future of computing. Turns out von Neumann architecture took over, but the theory stayed for a long time until eventually our computers caught up. So this right here, this massive beast, was that. One single perceptron that could listen to, this machine in particular was developed by the Navy. It would listen to a phone call and listen to 30 minutes of audio and then predict the next bit of information after that. So it wasn't super powerful, wasn't really cool, but it was a good start, and it really proved that the technology was possible, especially at the time. So as the technology's gotten better, we've moved from the single perceptron that we saw earlier to a combination of perceptrons. And again, this is one thing that we knew the theory. We knew that this was going to work far before we could actually do it. So really, a neural network is just a combination of that perceptron that I showed you earlier. We have our input layer over here, where this is going to be our input data, things that we want to look at. So the input for us seeing our parents' faces, and then intermediate neurons, which is going to do the majority of the calculations that optimizes or gives us the output that we want, which would be maybe output 1 is good, output 2 is bad. So fire, bad, parents' face is good. And inside that you can see here is a more modern version of the perceptron, which is just a node. So we have our weights that come in. So every single one of these nodes expands into this. So we have the weights that come in from the other nodes into the transfer function, which we're going to keep it super high level. You don't really need to know a whole lot about what that is. And then that goes into an activation function, which again, there's a lot of activation functions. We're going to use one here, and that's going to go out into the next node or to the output. And then this gets expanded even further as we began to be able to use GPU technology to be able to process faster and build larger networks like this. We were able to do a lot more with machine learning than we ever could before. So what I mentioned earlier, the thing that I'm going to do or live code demo for. By the way, live demos are notoriously bad. Live code demos are worse. So if I screw up, I'm just going to copy paste the code I already have. So this is our data set that we have. So the idea here, this is actually a very popular data set. If you use Google, Wisconsin breast cancer data set, it's a very well-studied and famous data set. The idea is 699 patients had a tumor biopsied. And these researchers took measurements on the cell, so the clump thickness, uniform cell size, cell shape, marginal adhesion, other biology stuff, I don't know. And they looked at that and thought, hey, with just this data, can we use, at the time, very primitive machine learning technologies to predict whether the diagnosis is going to be malignant or benign? And the intent was to do better than what a physician would do just looking at this data. So here's an example of how we're going to manage that data with our neural network. So all of these columns are our inputs. They're going to go into the input layer. We're going to have one or two, however you want to set it up, hidden layers in the middle, and then that's going to go to an output. In our output, in this case, we're going to be using a softmax activation layer. Don't need to know that, which is going to tell us, is it benign or malignant, and what is our percentage confidence in that? Are we 80% confident? Are we 50% confident? Do we have no idea? And so from there, that's where if you didn't get the repo, which is back here, if you're going to play along, copy this down real quick. If not, I'm going to show you the code demo. So I do have code printed out so I can read along, which is disgusting. It might be the first time I've ever printed code before, but right off the bat, we're going to use, oh, she's gone. She mentioned Pandas. It was very, very powerful and incredible library for managing data. So that's going to be the very first thing that we do is import all of our necessary libraries. So Pandas first. Then we're going to import Keras, which is, again, a very powerful and popular library. It's built on either Theano or TensorFlow. And the thing that's cool about that is TensorFlow and Theano are really, they're not machine learning libraries, which a lot of people think they are if you've heard of those. They're really just a good way to manage matrix calculations in linear algebra. And so what Keras does is takes TensorFlow or Theano, whichever one you choose, and then puts wrappers on top of that to use those functions in a way that is popular for building machine learning models. So you're not going to, if you're using Keras, you're not going to be building groundbreaking technology, but you'll be able to keep up there with most data scientists. So we're going to import NumPy, which most people know what that is for managing numbers. Yeah, sure, maybe. I guess I can probably just, yeah. Yeah, there we go. Is that good? All right. So we imported all Keras, but I'm going to go ahead and import two specific models directly. So our sequential model is what we're going to use from Keras for building the neural network. And then we're going to use two layers in particular. So dense and activation. So going back to the diagram you saw earlier, dense means specifically that every layer is interconnected with every other layer perfectly. So our first layer, every single node is connected to every single node of the next layer. That's the simplest version of a layer, which is going to give us the best results in this case. And then our activations, what I mentioned, the activation function. So we're going to use two. It's not super important, but that's how the layers are going to communicate with each other and into the output. And then finally, last one, we're going to use sklearn, which is kind of paradoxical, but they have better metrics than Keras does. So we're going to use that here. All right. That's cool. Well, we'll keep going. So beyond that, we're going to establish some config variables. Okay, here we go. Now we're going to establish some config variables, and this is important because it's going to help us decide or explain the theory and some of the big decisions we're going to make later on, which is what data scientists tend to spend a lot of their time on is these variables and tuning them appropriately. So actually, I'm going to do. So our test split is important. That is, when you look at the data set, we know we have 699 rows. That's 699 patients and different tumors that were biopsied. If we show the neural network all 699 of them, it has the capability of memorizing all 699 of them, and then when you see one later, it's going to say, hey, I remember that one. That one's benign. We don't want that, because you have a new patient that comes in and they have different data. It's not going to know how to handle that. So that's overfitting, and it's not giving us an accurate representation of its accuracy. So what we're going to do is split the data set. So we're only going to train on 90% of the data set, and 10%, we're going to round up to 70. That percentage of the data set is going to be reserved. The neural network will not see it, and then we'll test on it and see how does it do on data that it's never seen before. And that's going to give us a more accurate representation of how it would perform in the future on new patients. Our whole symbol is kind of important. There's some missing data in this data set. Don't judge my spelling. I'm really bad at spelling. I'm not going to lie. So there's some holes in this data set. We just have to manage that, and we'll get more into that later. Prediction column. So we care about, going back, I'm going to keep this up. Going back to our data set, let me zoom in on this a little bit. Of all these columns, the thing that we want to know is class. That's really all there is to it. So we're going to say we want to pull out class, and we're going to go ahead and define that here just so it's easier to see. And then how many epochs? So HM. Epochs. Some people say epochs. I like epochs. It's an ongoing debate. It's stupid. And we'll get more into that as well. Actually, so an epoch is how many times you look through the data set. So if you give the data set to the neural network and we look at it one time, it's going to look at each row and say, okay, this number comes out to this. It's going to use backpropagation, which we don't have to get into a whole lot, and learn, okay, we were this far off. I need to do this instead of that. Once it looks through all 699 rows, it's seen all of them one time. That might not be enough to train the neural network. It might not have learned enough in those 699 iterations. So we're going to go ahead and do it 10 times. So it's going to see each row 10 times, and it's going to give it a better idea as we repeat. You would rather have 10 times more unique data if you could, but since we only have the 699 rows, we're going to go ahead and repeat it. And that's another one of the things that you would optimize and tweak as you're trying to get a better accuracy. And finally, learning rate is the last hyperparameter that we're going to define here. So your learning rate is, once it sees the first patient, it will identify, okay, this set of numbers means benign. It will always mean benign. And then once it sees the next one, then it will learn, okay, well, actually, no, this one means benign, and kind of combine it. If you were to set learning rate to 1, every time it sees a new set of data, it's going to decide this is benign, or this is malignant. Once you set the learning rate to, I have it pretty low, 0.001, it's going to say, okay, well, the last one was benign, but this one's malignant, so we're going to tweak it just a tiny, tiny little bit and see if it gets better over time. And again, that's another one of the things that you would continue to optimize. All right, and now we're going to get into preprocessing. So preprocessing, unfortunately, it's my least favorite part of anything that I do. Is a very important part of data science. You'd think it'd be really cool you're building artificial intelligence and you're doing fun stuff, but really half the time you're just messing with SQL databases and trying to turn it into something that an AI can read or a neural network can read. And that's really important because a neural network can only understand information in certain contexts, or in certain contexts in certain ways. It can't read text. And when you're looking at text, if you're doing natural language processing, you have to find a way, how do you convert that text into something that the neural network can actually read, whether you're doing that through bag of words, whether you're doing that through word matrices or intent matrices, or if you're doing it through convolutional layers. Again, it's a little beyond the scope of this. You have to find some way to turn it into something that the neural network can understand. So that's really important here, and that's what almost all of our code is going to be here. So I'm going to go ahead and speed this up a little bit because we lost some time earlier. So I have all the code right over here. I'm just going to copy this in and run through it. First thing, we're going to import our data sets. We're using Python. Obviously, we're using Python. We're using Pandas here. So PD, we defined earlier, is Pandas. Read CSV, simple function. We pass in the data set. And then first thing we're going to do is go ahead and drop the ID column. Just going back to this, all of this data matters except for the ID. Who cares what the patient ID was? It doesn't affect the outcome. So we want to drop that so we don't have to worry about it. Ideally, the neural network would understand, hey, that doesn't matter. We'll just ignore it or put a very small weight into that input. But we can skip that just by dropping it all together. I'm going to skip on to the next one. I'm just going to do a whole chunk of code. Plus, typing up here is dangerous. Oh, man. Yeah, there we go. Does it run with these? Does anybody know? We'll give it a shot. We'll see what happens. No? Okay, cool. Okay. Let me, we don't have to get into that. Oh, dang it. Okay, I was gonna switch to raw, but I don't have internet. That's fine. Okay, see if hopefully this runs. Here. So what we're doing here, going to dive into the code a little bit more rather than just watching me manage tabs. So the intent here, you can see in the comment, is to remove the holes and replace with the mean. So what I mentioned earlier about the whole symbol is a question mark. So on the data set, there are certain things, like maybe for this patient, we were unable to get the uniform cell size, whatever it may be. There's no way to get that data, so we're going to fill it with a question mark. The neural network can't understand a question mark. It can only understand integers. And so from here, we're going to replace it with something. In this case, we're doing the simplest thing where you replace it with the mean for the column. So ideally, it's going to be as far away as an outlier as we can. It's going to be data that is not going to change the results in any way. There's better ways to do it, but the mean's pretty simple. So we're going to loop through all the columns, pull out the numbers, anything that's not a question mark. We're going to find the mean from that, create a new column, and replace anything that's the whole symbol with that mean. So if the average for uniform cell size is 5, anytime there's a question mark, we'll throw in a 5 there. And after that, we are going to split the test and train set. So we mentioned that earlier. We're going to do 90 and 10%. Boom, there we go. So that's really simple. We're just going to say our test split's 1%. We're going to make test rows, the length of it times the 1%, or 1%, the 10%, 0.1, and then subtract that to get our train rows. That's pretty straightforward. And Pandas has this cool function where you can take the integer, and it's basically the same thing as that, but with tail and head, or head and tail. We run that. Okay, and then we're going to split our inputs and outputs. This is where it gets a little wonky. Like I mentioned earlier, you have to process the data in a way that the AI can understand, and that's coming in and it's coming out. Oh, we're not there yet. So the other thing that we're going to do, so we have to split up our inputs and outputs. That's pretty obvious. So going back to our diagram here, we have all of our inputs on the left side, and that's going to be, even though the data is in the same data set, we need to put it into its own array, and we need to put the output into its own array. So we can say, in this array, in the input array, index 35 is going to match with the output index 35. So it's still very straightforward, and if you want to look at the code more in the repo, you're more than welcome to. So I'm hoping that this is not going to throw any errors. And every time I click that button, my heart skips a beat. Okay, and here, this is where the output gets a little bit more important. So let me fix these. Okay, so the output, going back to our diagram, what we could do is, since it's 2 and 4, let me go back to that as well. So in our data set, we have the two classes. The class is either 2 or 4. And in this case, 2 corresponds with malignant, or no, 2 is benign, 4 is malignant. So we could just predict 2 or 4, but say it predicts 3.999. Sure, that's 4, but what if it's 3? We don't have a good way to understand, like, is it saying that it's not sure, it's 50% confident, and that's not something we can infer from that. So instead what we'll do is assign these to independent variables. So we're going to have a one-hot encoded array. I'm going to run this and put a markdown in here. So we have a one-hot encoded array. So our basic array is going to be 0, 0. 0, 0 would be there's no class assigned. 1, 0 would be, benign. So that's going to correspond to 2. And then 0, 1 is going to correspond to malignant. And so ideally, the neural network is going to see the inputs. It's going to see 5, 4, 4, 5, 7, 10, 3, 2, 1. It's going to look at that, and then it's going to give us, the correct answer is 2, so we want this. So maybe it says 0.33, 0.66. that's going to say it's 66% confident that it's malignant. We're going to say, no, it's actually 1, 0. It's going to use those numbers, backpropagate, and learn from that using reinforcement learning. And so that's what we're doing here. We're simply going through every output and assigning it a one-hot encoded label based on whether it's 2 or 4. So from there, I'm kind of blowing through this now since I'm copy-pasting, but that's fine. All right, from there, we're going to do the same thing with our test set. Probably could have done that before and just done it to both, but whatevs. Yeah, OK. We lost a lot of time, so I'm trying to make up for that. I don't know what this is going to do. Cool. OK, from there, we get to the exciting part. So creating the neural networks, obviously, the part that's a little bit more exciting than just managing data. So once we create the neural network, it's really simple. It's literally this many lines of code. And that's because we're using Keras. So typically, if you're using TensorFlow or Theano, it's going to be a lot of math. It's going to be a lot of setup. And that's fine. If you want to do super tweaking, you want to mess with small little variables, whether you want to do random initialization or if you wanted to change maybe a specific weight on a certain node or pluck a node out, you'd have to do that. But with Keras, we want dense layers. We want something super basic because this is an easy data set, and we'll see what we get. So first thing we're going to do is create the net. And sequential, you remember up here, we imported sequential from Keras. That just means that every layer has another layer after it, which is another layer after that. There's no splitting. There's no puzzle there. And then what this is a jumbled mess, but basically what this is going to do is clear the existing graph if there was one. So if you're running it over and over, this is going to make sure that there's no existing memory in there. And that's more important for a GPU, which my laptop does not have. It's on board. Okay. And here's where the magic happens. And I can imagine that it's relatively surprising if you come into this and you're like, machine learning is so far out there, and you see this and you're like, that is 4 pathetic lines of code. That is nothing. And really, the theory can be confusing. It depends how far into it you get. But this is the code using Keras. So net add, we're going to add a dense layer. Again, a dense layer is every node is connected to every other node. We're going to use how many inputs, which is we have 9 inputs and 1 output. So we have 9 nodes in the input layer. And then our input dimension is going to be another 9 nodes. So in this case, in this example, I should have just matched this. No. This. So we have our 9 inputs, and we're going to have a second layer of 9 as well. So they're going to be 1 to 1. And then we're going to have our hidden layer. And for whatever reason, when I wrote this, I decided 14. I don't remember if I tweaked it or what. So our hidden layer is going to have 14 nodes. They're all going to be interconnected forward and backwards. And then finally, we have our output layer. So our output layer is going to have 2 nodes because we have benign and malignant. And we're using the activation function softmax. And so the reason why softmax is so important in this case is typically, if you were to I shouldn't say typically. Traditionally, before we had activation functions and before this technology had improved, you would have one output layer, and that would predict the 2 or the 4, like I mentioned. And that really limits you because you can't infer the confidence of it. Softmax, what that's going to do is maybe benign is 272 and malignant is 17. Softmax is just going to limit each of them to say, OK, now you're going to be on a scale between 0 and 1. And collectively, every output node needs to add to 1. And then from that, you can infer the confidence. So that's fairly simple. We're going to compile the network. We don't have to get into this. We're going to use RMS prop, categorical cross entropy. So that's our loss function. What that is when you touch fire that's bad, it hurts. That's really all that is. So when it's off, if it's, say it's malignant, and it guesses 100% sure that it's benign, that's going to hurt a lot. And it's going to learn from that. And as it gets closer, it's going to learn a little bit less because the loss function is going to be further off. And then metrics, we're going to pull in accuracy because we want to know accuracy rather than if you were using another data set, you might use something else. And finally, we're going to train it. So that's really all there is to it, and it's shocking. So we're going to fit it, net.fit. We already created up here in our preprocessing. We created capital X, lowercase y. This is a convention a lot of people use. I don't really know why. Capital X is our input data. Lowercase y is our output. And we're just going to give it to that. So capital X is our input. Lowercase y is our output. And fx, this is where we choose. We chose 10 earlier. We could change it to 11. It would make very little difference. And then finally, we're going to do y scores. Net.predict. So this is, again, the neural network. We're going to run data through it. And the data we're running through it is our test data. So this is an array. It's just going to go through and produce an array of equal length of the output of everything we input into it. And then we're going to compare. First, we're going to convert that into the one hot encoded data that we want. And then we're going to compare how did that do against what the data set actually says for the data that it's never seen before. And so we'll run that. Here it is training. We ran 10 epochs. It's super quick because it's a tiny data set. And there's an error. Cool. Let's see, did I miss it? I think I missed this earlier. I'm just going to have to rerun the whole kernel. Yep, I did. Yeah. Let's rerun the whole thing just in case. Oops. This import's gonna, it didn't do it. Wow. Hey, that's what it is. When you're up here and you have people looking at you, your brain operates at 10% capacity, so please don't judge me for that. There we go. Okay, here's our training. And so in here, if we were doing a cooler data set that had more data, it'd be a little bit cooler because we'd have the first one would pop up and then the equal sign would slowly move along. It's also really infuriating when your day consists of just watching that equal sign move for 8 hours. It's pretty awful, but it's still cool to see the first time. So here's our loss function. This is our categorical cross entropy. So this is going to tell the neural network how far off were we and how should that number be interpreted. And our accuracy for the first one was about 50%. So it had a 50% chance. It was either benign or malignant. It just kind of took a guess using randomly initiated variables, and that's what it got on the first epoch. After the first epoch, it trained on our 630 example rows or training rows. And then it did the back propagation, where it said, okay, how far were we off? What happened? And let's learn from that. Did that 10 times, and you can see, we could plot this, but it'd take more time, and I'd probably mess it up. But we started with a 50% accuracy, and every epoch it slowly got better and better. And if you did plot it, you would see kind of a curve where it would die off. And that's where, if you were to put 100 epochs in, it would get better than 91%. That's actually kind of low for this data set, but it'd probably get to 95, 98%, and it would just taper off and just sit there forever. And that's where you really have to worry about overfitting. The data set starts to memorize the data, and it doesn't know how to understand any new inputs or data. And then the cool part, so we want to test it. So we know that based on the output data, no, first let's get the accuracy on the testing data. Dang it. So this 91% right here is the accuracy on the testing, or on the training data. So we don't care about that as data that it's seen. We want to see how it does on the testing data. So we're going to run that. You got 100%. That's, I hope that's right. We'll see. So in that case, of all 70 or 69 examples that it has, it got all of them right, which is very possible. I've never seen it for 10 epochs, but sure. And again, since there's a lot of randomly initiated variables, it changes every time, and that's totally possible. And then what we're going to do is actually try it out manually and see what happens once I fix this. So while true, that's a disgusting thing to do, but makes it easy. And what we're going to do is put in a string, we're going to split it on the comma, we're going to turn that into an inference tensor, send that, or we're going to reshape it so then it becomes a two-dimensional array, and then we're going to send that into the neural network with the same predict function we used earlier to get our accuracy, wherever that is, yeah, right here. And so this is why, say you built a machine learning system and then it was implemented in another system for ongoing use. Say at work you put it into your, I don't know, your website's backend. You wanted to predict what is this user going to buy next, or based on their recent history, what's the next page they would browse to, whatever it may be. You would run this function right here. You would say net.predict, pass in the information about the user, and then it would output whatever it predicts. So let's go ahead and use data from our data set. And let's use the first one to make it easy. So we got 511, 121. I don't want to look at all of them. 3, 1, 1. Okay. Ideally, this is fingers crossed. This is a moment of truth. Ideally, it's going to tell us 2, or it's going to tell us the the first number in the encoded array is going to be greater than the other. So boom, there we go. OK, so this is exactly what you see here with these two outputs. So benign is our first one. It's 79.7% confident that the prediction for this specific tumor is benign. And the opposite would be the 20% that it thinks it's malignant. So ideally, you'd want that number to be a little bit more confident. That would come with training and tweaking the model. But it's still pretty cool. And based off of this, we know that, or based off of this, we know that for every single one of the testing data, it predicted the accurate answer for whether the tumor was benign or malignant. And that's using a super simple beginner-level machine learning framework, something that you can, it's literally like, look at this, 4 lines of code that basically is English, and you're predicting the results of tumor diagnoses. Like that's pretty cool. It's a simple data set, but just if you take this, you learn, and you continue to grow with machine learning, and you continue to look at other implementations, there's so much that you can do, and it's not any more difficult than typical development. I think that's really the point that I really wanted to drive home today, was that so many people have that mental block. Like I mentioned in the beginning, they have that mental block that machine learning is so far beyond regular development. You have to have a PhD, you have to have whatever to be able to understand it. And with modern libraries, you can get started super easy and then transition into the stuff that requires a PhD, or doesn't require, that traditionally required a PhD. You can transition to TensorFlow, you can transition to Torch, whatever it may be, if you want to switch to C++, C, because your work says Python's dumb because they're wrong. But that's really the point I wanted to drive home, that we're doing something so cool with machine learning here with 3 lines of code. And you can do that with your own implementation, with your own startup idea, with your own whatever at home tonight if you wanted to. So that's all I got. But, yeah.